Have you ever stopped to think about how your favorite whiskey gets made? Or how we get something like gasoline out of crude oil? Well, the answer to both is a process that is old as it is elegant, and it's called distillation. Today we are diving deep into this fundamental science of separation, and trust me, it shapes our world in ways you probably never even realized.
Okay, let's start with a classic thought experiment. Picture this. You're stranded, surrounded by the ocean, you're thirsty, obviously, but all you have is salt water. So how do you turn that into pure, drinkable water? Well, the solution is actually way simpler than you might think.
The answer, of course, is distillation. It's this beautiful solution that really hinges on one simple, powerful idea. Different liquids turn into gas at different temperatures, and if you can control the heat just right, you can pull them apart. It's all about mastering that change of state.
All right, so how does this whole thing actually work? Let's break down the core principle of what's happening.
It all unfolds in 4 key steps. First, you heat up your mixture. Now, the component that's most eager to become a gas, the one with the lower boiling point, vaporizes first. This vapor then travels up and into a cooling tube, which we call a condenser, and that's where it turns back into a pure liquid. And finally, you just collect that purified liquid, the distillate, in a new container, leaving all the other gunk behind. Simple as that.
So that's the what. We get it. But to really understand this, we need to dig into the why. And it all, and I mean all of it, comes down to the science of boiling.
It all kicks off with something called vapor pressure. And honestly, the best way to think about it is escape pressure. See, inside any liquid, all these little molecules are constantly trying to break free and turn into a gas. Things that escape really easily, like alcohol, we call them volatile. And that just means they have a high vapor pressure. They're ready to go.
So what is boiling then? Boiling happens at a very specific moment. It's the exact temperature where that internal escape pressure, the vapor pressure, gets strong enough to equal the pressure of the atmosphere that's pushing down on it from the outside. When those two forces are perfectly matched, boom, the liquid can finally boil freely.
And this is the key takeaway, the most crucial part. The higher a liquid's vapor pressure, the lower its boiling point. It just makes sense, right? A substance that's already eager to escape doesn't need a whole lot of heat to make the leap. This difference, this is the secret sauce of distillation. It's the gap that we exploit to pull things apart.
All right, theory's cool and all, but what does this actually look like in a real lab? Let's see how it works in practice.
Now, for a basic, simple distillation to work really well, you need a pretty big difference in the boiling points of your liquids. The general rule of thumb in a lab is you want a gap of at least 70 to 80 degrees Celsius. That big gap ensures that when you start heating the mixture, one substance completely vaporizes long before the other one even gets close to boiling.
And this simple method is absolutely perfect for a few key jobs. Think back to our saltwater example, right? You're removing a non-volatile impurity, the salt, from the volatile water. It's also fantastic for boiling off a solvent to get back some compound that was dissolved in it, or for just cleaning up a liquid that's got a few stubborn, high-boiling contaminants mixed in.
But what happens when that nice, big 70-degree gap just isn't there? What if the boiling points are super close? For those tricky situations, chemists have to pull out a more powerful technique, fractional distillation. It's basically like running many distillations all at once, in a single column, which allows for a much finer separation.
But, sometimes chemistry just throws you a real curveball. For the absolute toughest separation problems, chemists need some pretty advanced techniques up their sleeves.
Okay, here's a real head-scratcher for you. What if the very act of heating a substance up to its boiling point completely destroys it? How in the world do you purify something without basically cooking it to death?
Well, the solution is just brilliant. It's like if you can't change the liquid, change the air around it. Remember how boiling is a fight against that external pressure? Well, by putting the entire setup under a vacuum, you dramatically lower that external pressure. This makes it way easier for the liquid to boil, often at temperatures more than 100 degrees Celsius lower than normal, which safely protects those fragile compounds. It's genius.
All right, let's talk about another tricky scenario. What do you do when you have a mixture of two liquids that are just stubbornly stuck together? No matter how carefully you try to distill them, they just refuse to separate. This incredibly stubborn mixture has a name. It's called an azeotrope. And it's this super weird quirk of chemistry where two liquids, at a very specific ratio, basically team up. They start acting like a single brand new substance, boiling together at one constant temperature.
And that, of course, makes separating them with normal distillation completely impossible.
But you know what? Chemists are a resourceful bunch. They figured out all these clever ways to break the azeotrope. Sometimes, just distilling under a vacuum can shift the boiling points enough to pry them apart. Other times, they might use another liquid to literally pull one of the components out. Or they'll add a third substance that just messes up their chemical interactions. In really extreme cases, they might even chemically react one of the components to turn it into something else entirely, which makes the separation a piece of cake.
Okay, we've been deep in the science. So let's zoom out for a second. Why does any of this matter so much? Not just in the lab, but, in the world all around us?
Getting that perfect, pure substance, it takes some serious precision. In the lab, every little detail counts, from checking for the tiniest leaks before you start, to insulating the glassware with foil, to making sure your water condenser is hooked up just right for maximum cooling. It's a great reminder that even a process this powerful still relies on careful, meticulous execution to get that perfect result.
The power of this one single process is absolutely staggering when you think about it. In a chemistry lab, it's used every day to prepare ultra-pure solvents or to pull water out of a reaction. It's the key to steam distillation, which is how we get fragrant essential oils from plants. And on an industrial scale, it's the backbone of oil refining, separating crude oil into gasoline, jet fuel, plastics, and of course, bringing it full circle, producing clean, fresh drinking water from the sea.
And this isn't some brand new cutting-edge tech. Far from it. Distillation is one of the oldest scientific methods we have. It's a fundamental tool that humans have been using and refining for centuries to separate the things that want to fly away from the things that want to stay behind.
So I'll leave you with this thought. At its absolute heart, distillation is a relentless search for purity. It's a process of heating, transforming, and condensing something down to its most essential form, leaving all the impurities behind. And it kind of makes you wonder, what other messy mixtures in our world, whether they're ideas or systems or anything else, could benefit from that same clear, focused process of separation? Thanks for joining me.